Hello, and welcome to the third video of the FP2 chapter Maclaurin and Taylor series. Start a question on the screen here to get us going for this video. Use a Maclaurin series expansion to expand the function natural log of x. So at the bottom here we've got the Maclaurin series. We need to find f of 0, so we put 0 in here, and that gives us log of 0, which is a problem because that is undefined. And if we were to continue, we would have the derivative of this, which is 1 over x, 1 over 0, which is also undefined. Oh no, we have a problem here. We cannot use the Maclaurin series expansion to expand this function because these are not defined when x equals 0. So on the first video I said that there are some functions where this won't work. This is one of them. In this video we're going to look at how to get around this. We're going to use the Taylor series expansion. There are two forms, we're going to look at both. So some functions and or their derivatives will be undefined when evaluated at x equals 0 and so cannot be used in the Maclaurin series expansion. Colin Maclaurin, however, was actually using a specific application of Brooke-Taylor's more general series, which is what we're going to look at today, evaluated at any point x equals a. It does not need to be 0, although to be fair, 0 is often the easiest point to use if it does work. So over here we've got Maclaurin. He used Brooke-Taylor's series and put x equals 0 to make Maclaurin's series. So this is the more general version. The Taylor series expansion is given as this. Now you can see a slight difference here. We've still got a constant here, but it's f of a now instead of f of 0. Obviously if a equals 0 you can see where that comes from. And then here the first derivative evaluated at a times x minus a. And again if a is 0 you can see how this collapses to the Maclaurin series. But if a is not 0, what we end up having here is a series expanded in powers of a bracket, not powers of x, which is really interesting and sometimes not as useful. So there is actually a second form of Taylor's series to get powers of x instead of powers of a bracket, but still not using 0, and we can do that by replacing x in the function here with the expression x plus a. So if you put x plus a in here, then all of these x's become x plus a, and obviously x plus a minus a just gives you an x. So the second form of Taylor's series expansion is this. So that means we've got three different forms of what is essentially the same thing. This is Maclaurin's series here, Taylor's, and Taylor's second form here. So if you take this one and you put x plus a in here instead of x, you get this one, and in either of these, if you put a equals 0, you get this one. So they're kind of all the same thing. But having them separate in your formula booklet is quite useful. And while only Maclaurin series is in the UK formula booklet, they are all in the international formula booklet. It's quite useful because the A-level exam questions make it very clear what to do on these sorts of questions, and therefore which starting point is the most useful. So we'll do a few quick examples. We'll do one for this and two for this. Here we go. Find the Taylor series expansion of the natural log of x, the one we could not do for Maclaurin's in the starter question, in ascending powers of x minus 1, as far as the term in x minus 1 cubed. So you can see here in the question it's very clear, find the Taylor series, not the Maclaurin series, so that's one of these two. And then in ascending powers of x minus 1 makes it very clear that it's this one here, not this one here. So we know which starting point to use. We also know the function. We've got f of x is equal to the natural log of x. Then the derivative of this is 1 over x. The derivative of that is minus x to the minus 2. And the third derivative, because we know from the question we need to go up to power 3, is 2x to the minus 3. Now we need to evaluate each of these, but not at x equals 0, because that was the very problem with Maclaurin series, we can't do that. Here we're using x equals 1. Be careful, don't use -1. The minus is part of the formula. So here a is equal to 1. So we're evaluating each of these at 1. And this is not a problem. We can do this for each of these. Get -1 here. And here we get a 2. So you can see it's very similar to Maclaurin's series, the process. We're just going to take all of these and put them into the appropriate formula at the top here. So we've got natural log of x is equal to the first one, the function evaluated at a is 0, and then the derivative evaluated at a is 1 times x minus a, where a is still 1. So we get 1 lot of x minus 1, and then we have -1 here divided by 2 factorial times x minus 1 squared, and then 2 for the next term in here, 2 divided by 3 factorial times x minus 1 cubed, and that's as far as we need to go. So here, just tidying this up a bit, x minus 1 minus 1 over 2 x minus 1 squared plus 1 over 3 x minus 1 cubed. Don't open those brackets. The whole point is that we're having it in terms of these brackets, but do simplify your coefficients. So that is the final answer. Second example is very similar, but we're going to use the other formula. And you can see that here quite easily by noting that it's sine not x, but x plus something. So here we've got the function of x plus something, and then it just reiterates that by saying in ascending powers of x. So we don't want brackets here, we want powers of x, and because there's an x plus something in the function, it's clearly Taylor's expansion, even if they hadn't said here, use the Taylor expansion. But they have told us the answer, so we can check our answer at the end, matches this in the question. Going through this same process, the function is sine of x. Now be clear here, don't use x plus pi by 6 here. The function of x is sine of x. This is still what we're using to find all these bits here. The only difference is that at the end we will put sine of x plus 6 as this part here. So don't get confused, don't use this to find your derivatives. The derivatives are still coming from the function of x, which is sine x. So the first derivative of that is cosine x. Second derivative takes us minus sine x. And we need power 3, so we need the third derivative, which is minus cosine x. Now in this question, we can see from here that a is equal to pi by 6. So I need to evaluate all of these at pi by 6, which is 30 degrees, so sine of 30 degrees I know is a half. The derivative cosine pi by 6 is root 3 over 2. And then we get the same numbers here, but with a minus sign. Okay, so we've got all the information. Now we just need to put it into the expression and put at the beginning here sine x plus pi by 6. So we've got sine of x plus pi by 6 is equal to the function evaluated at pi by 6, half, plus the derivative at pi by 6, root 3 over 2 times x, plus the second derivative at pi by 6, which is minus a half, divided by 2 factorial times x squared, and then the third one here would be the third derivative divided by 3 factorial times x cubed. And that's where we stop. Tidying this up again gives us a half plus root 3 over 2 x, and a half divided by 2 is a quarter, so we've got x squared over 4, minus root 3 over 2 over 6 is root 3 over 12, x cubed, and then double check that does match with what we had in the question. It does, yes. So from those two, I hope you can see that the process is very, very similar. We're using f of x each time, even if we're expanding x plus something, and then we're evaluating at x equals a, putting all the information into the appropriate formula. It's very similar to the Maclaurin expansion process. Final example then has a little bit extra. We're going to express tan of x plus pi by 4, so we are going to use this one again, and then we're going to use it to find an approximation for tan of pi by 3 in terms of pi. So to begin with, very similar, we are going to use f of x is equal to tan x. The derivative of tan of x is sec squared x. The derivative of sec squared x, if I bring the 2 down the front, to sec x times by the derivative of sec x, which is sec tan, so there's another sec there and a tan x. So I've treated this like a bracket and brought the 2 down the front, so that's 2 sec to the power 1, but then when you differentiate sec using the chain rule here, you then have another sec coming in and a tan coming in. Take a moment to do that yourself if you'd like to make sure that's right. The third derivative, because again we're looking for powers up to 3, is equal to the derivative of this thing here. Now I'm going to have to use the product rule. So if I leave tan x alone for a moment and differentiate sec squared first, we've actually already done that here though. Differentiating sec squared gave us this expression. So if I differentiate sec squared here, I'm going to get the same expression, but I've got a tan x as well already there, so that's going to become a tan squared, and I've already got a 2, so that 2 will become a 4. So we get 4 sec squared x tan squared x, and then if I leave sec squared alone, I've got to differentiate tan, which we've already done here as well. So differentiating this will give me sec squared, and there's already a 2 sec squared there, so that term will become a 2 sec power 4x. And again, if you're not happy with that, take a moment, pause the video, go through the product rule, differentiate this, you should get this expression here. Now we need to evaluate this at x equals a, where a is pi by 4. Pi by 4 is a nice number to use in tan because it is just a 1. It's a bit more complicated in cosine. It's a root 2 over 2, and that should give us a 2. This one, evaluated at pi by 4, you can stick that on your calculator, or you can use the fact that we've already got tan x and sec squared x evaluated for us here, put these in here, and that gives us a 4. And then the third one, same again, on your calculator if you want to, but there is enough information here to put it in here, and that should give us an 8 plus an 8, which is a 16. So we've got all the information now. We need to put it into the formula, and we are expanding tan x plus pi by 4 to give 1 plus 2x plus 4 over 2 x squared. 1 plus 2x plus, let me write 2 factorial still for a second, x squared, and then the third one is plus 16 over 3 factorial x cubed. Simplifying those two fractions, we get 1 plus 2x plus 2x squared plus 16 over 6, which is 8 over 3x cubed. And I've used an equal sign there, so plus dot dot dot. And there is our expansion. Now we need to use it to find an approximation for tan of pi by 3 in terms of pi. So using tan of pi by 3 in this expansion here, that doesn't quite match yet because we need x plus pi by 4. And at the moment we don't have a pi by 4 here. We need to split this into two pieces, something plus pi by 4, which is equal to pi by 3. And if we do that, we end up needing pi by 12 plus pi by 4. In order to match this to this style of expression, we need to write it like this. So the pi by 4 matches the pi by 4, which means x must be pi by 12. So that's telling me x is equal to pi by 12. So then I can use this expansion. Knowing that x is pi by 12, we put it in here, here, and here, and that gives us 1 plus 2 times pi by 12 plus 2 times pi squared over 12 squared, which is 144, plus 8 pi cubed over 3 times whatever 12 cubed is, plus dot dot dot. Grab your calculator. 1 plus pi by 6 plus pi squared over 72 plus pi 3 over 648. And this is our expansion in terms of pi for tan of pi by 3. Now if you take a moment and think about this, this is really quite amazing, because the tan of pi by 3 is the square root of 3, if you just put that on your calculator. So this is telling us an infinite series in increasing powers of pi for the square root of 3, which begs the question, can all surds be written as an infinite series in terms of increasing powers of pi? That's a question I will leave for you to investigate. A quick summary then. We've done 3 major things: Maclaurin series here, Taylor series here, and the second form of Taylor's here. And then we've also got in the formula booklet these 5 specific examples of Maclaurin series given to you to use. All of these are in the international formula booklet, and all of the ones in yellow are in the UK formula booklet. You don't need to remember them, but you do need to know which one to use when. Big clues in the question for that. Read the questions carefully, and of course you need to know how to use them, being able to manipulate them as we've done in the examples. Maybe I'll see you in the final video applying these ideas to differential equations. In the meantime, you can practice questions from exercise 7D.